Ladies and gentlemen, good afternoon. My name is Lia Ferrari and I'd like to present you a paper titled From Art to Science of Construction, the Permanence of Proportional Rules in the Strange Case of 19th Century Ponte Taro Bridge, Parma, Italy. First of all, I would like to thank my co-authors from the University of Parma, Professor Federico Ottoni and Eva Coisson, and the architect Luca Braglia. It is well known that empiricism has been at the base of the main architectural construction up to the 17th century. But actually, this geometrical method for structural design has been used, in particular for bridges, at least until the beginning of the 19th century, despite the availability of the newborn building science theories. Following the empirical approach, each improvement or dimensional change in correct ancient constructions, and those arrived to us definitely are, is due to a significant technological enhancement, allowed it by the observational method, thus understanding previous failures and solving constructive mistakes. Despite their massive appearance, masonry structures are essentially not isostatic. As Milani highlighted at the beginning of the 20th century, the stability of monolithic masonry structures depends on equilibrium. So overturning occurs when the resultant falls outside the wall thickness. Therefore, the geometrical ratio between thickness and height is a fundamental parameter in order to state the stability conditions against horizontal forces, such as the thrust of arches. The application of the proportional theory is particularly interesting in the case of bridges, which bring together dimensional issues with technical construction problems. In this regard, the size of pillars represent a central theme, since they must have the right thickness to resist the thrust of arches and, at the same time, to allow the passage of water. So, if we consider the dimensional prescription for bridges in terms of walls or piles thickness compared with their span, we can notice the permanence of similar dimensions over time. The progression of these structures is indeed more evident in the technology used for building. Leon Battista Alberti declared, for instance, the importance of reinforcing the filling of vaults and of using large-sized blocks to ensure masonry stability while reducing the pile thickness for hydraulic efficiency. Therefore, only the occurrence of both the respect of ancient dimensional rules and the use of proper technology in the arrangement of material and in the wall construction can constitute a reliable qualitative method for expeditious stability analysis of historic bridges, thus anticipating the result of further limit analysis. The case study of Ponte Taro Bridge near Parma in northern Italy is here presented to show that on one side the respect of proportional rules can be a first guarantee of stability, and on the other side the non-respect of technological prescriptions central in the bridges could be the cause of damage. The bridge is a very important monument both from cultural and strategic point of view, and moreover it is an interesting case study not only for the technical and structural issues related to its restoration and use with increased traffic loads, but also for the role that geometry played in its history and stability. The bridge was commissioned by Maria Luigia, Duchess of Parma, and it was built between 1816 and 1821, according to the design of engineer Antonio Cocconcelli. The original configuration was composed by 17 arches but after a flood in 1818, it was modified, adding 3 arches and deepening the foundations. So, the final bridge consists of 23 centered lowered arches with 24 meters span, supported by rectangular pillars rounded on the short side to reduce water impact. The pillars lay on timber posts as foundations. Oculus have been inserted above each pillar, easing the outflow of water, whereas the external brick structure unfolds an internal filling of river cobblestones mixed with mortar. Nowadays, the bridge is still in use, although it is too narrow for the modern traffic requirements, not ensuring a safe passage. The upper parts, especially the roadbed layers and the lateral walls, have undergone several works in the last decades, as well as the bottom foundation elements that were consolidated to improve their stability with regards to the water flow actions. Conversely, the conservation problems of masonry arches have been rarely faced in the past, and now their poor condition worries about possible structural problems. So the current decay phenomena of the masonry surfaces were mapped on the photogrammetric surveys, and the uneven distribution of these decays suggests meaningful indication about their possible origins. Widespread efflorescence are present at the intrados of the walls, probably due to de-icing salts percolation in the inner part of masonry because of the ineffective drainage system. Moreover, missing or detached parts of masonry have been identified at the edge of the vault and the arch front elevation. This disorder could be related to the brickwork disposition, possibly worsened by structural stress concentrations. Furthermore, some cracks have been detected. Some of them are clearly due to reconstructions carried out after World War II or car accidents, whereas some other fractures seem to be related to the typical depressed free-centered arch mechanisms or to different settlement of the walls. So, to verify this hypothesis, the present geometry has been analyzed, searching for differential settlements both longitudinally and transversally to the bridge. Actually, comparing the pier top levels, the differential settlements turn out to be quite limited, and this data, in compliance with the result of geological tests, prove the effectiveness of the previous underpinning intervention of the central pier's foundations. On the other side, the arches instead show more significant deformation. Therefore, the current survey and the original design shape deduced by Concelli drawings were compared, and 7 out of 20 arches highlighted a lowering of the keystone higher than 30 centimeters. This value seems to be due to further movements occurred after the physiologic lowering of arches during the centering removal in the construction phase. To evaluate if the longitudinal cracks could be connected to some torsional effects, a further comparison between the levels of the keystone in the north and south arch of each span was performed. Most of this inclination proved to be southwards in the west side of the bridge, changing northwards in the east one. So finally, comparing the crack pattern and the deformation analysis, it is possible to find a correlation between the fractures and the settlements only in 2 arches, those highlighted in red in the present slides. This fact leads to speculate that the damage is not structural but more probably linked to local mechanisms ascribable to as many defects during the construction phase, particularly significant in the case of bridges with independent arches as the case study. To verify the stability by means of a simplified and qualitative approach, an integrated analysis of the historical proportional theory and the constructive features of this peculiar masonry bridge was carried out. First of all, the adherence to the prescribed proportional rules, recalled at the beginning, was verified to ascertain the respect of Cocconcelli prescription for the ratio pile-span equal to 1/6, as shown in the figure in the lower part. Actually, what we can notice is a slight license in the thickness of the arches. The engineer here applied a smaller ratio than the one prescribed by treatises. These advancements were made possible thanks to Mery's method used by Cocconcelli for designing the bridge. So, recovering this graphic analysis, it was verified that the curve of pressure is all contained in the middle third of the arch thickness, thus guaranteeing the best behavior for masonry. The same result has been obtained by applying simplified limit analysis to the wall arches, as shown in the left image. The safety factor, intended as the ratio between the thickness of the arch and the minimum one to contain the pressure curve, was found to be well above the collapse limit stated by Heyman. Further simulations were performed with worse conditions. Firstly, considering the arch itself without the additional load as shown in the upper right image, and then adding another symmetrical load in the right bottom part. In these cases, a sensibly lower safety factor was found, however far above the minimum required for stability. So, the case study shows a surprisingly high load-bearing capacity despite the load having significantly increased over time, thus definitely confirming the reliability of Mery's graphic method. In conclusion, we can see the history of constructions as the translation of structure into geometry. The panel shape of ancient buildings used to be the formal result of an empiric calculation. So instead with this, a specific interpretation of the geometrical survey data can represent a powerful tool for the comprehension of the present structural condition, as well as a precious element for the validation of any further numerical models. Moreover, retracing and recovering the principles, both dimensional and technical, which governed the design and the construction of these ancient buildings and infrastructures, this can be considered the first step to reliably interpret, even if in a very simplified way, their current damage and residual behavior, which is the first condition for setting up an effective strategy for structural strengthening. So, thank you for your kind attention.